Hi, and welcome to day 23 of Just Start Programming, the Rust programming language. Today's topic is the continuation of smart pointers, and I think this would take us more time than the other concepts. So there's a possibility that I will have several streams based on this topic. And no, we're not stopping as we have already invested a lot of time. So let's carry on and push forward. Join me once again, do it live in one take, no shortcuts and no secrets. Well then, let's just start programming. Okay, so before we start with the new topic, let's just review once again what are smart pointers. So let's come back and glance through what we have here. So you have pointer and you have smart pointers. So pointer addresses refers to or points at some data. So we've covered that in chapter 4, indicated by the ampersand symbol and borrow the value they point to. They don't have any special capabilities other than referencing to data, and they have no overhead. Smart pointers, however, are data structures that act like a pointer but also have additional metadata capabilities. So it says here it's not unique to Rust. It originated in C++ and exists in other languages as well. So Rust has a variety of smart pointers um, defined in the standard library that provide functionality beyond that provided by references. They also have reference counting smart pointer type. So it allows data to have multiple owners by keeping track of the owners, and when no owners remain, cleaning up the data. Okay, concept of ownership and borrowing. In many cases, smart pointers own the data they point to. Okay. Few smart pointers in this book, including string and vector. So we covered that in chapter 8. Both of these types count as smart pointers. So string and vec are smart pointers. They own some memory and allow you to manipulate it. They also have metadata, extra capabilities, or guarantees. Okay, string, for example, stores its capacity as metadata and has extra ability to ensure its data will always be valid UTF-8. They are usually implemented using structs. Unlike structs, smart pointers implement deref and drop traits. So the behavior of dereferencing and dropping. So traits is the interface. Deref trait allows an instance of the smart pointer struct to behave like a reference, so you can write your code to work with either references or smart pointers. The drop trait allows you to customize the code that's run when an instance of the smart pointer goes out of scope. It's like garbage collecting also. In this chapter, we'll discuss both traits and these traits and demonstrate why they're important to smart pointers. Okay, so here we'll cover the most common smart pointers in the standard library, boxt. I think we did boxt the other day. And this one, rect, I think Reference, okay, reference counting type. I think we will do that somewhere here. Ref T and ref mut access through ref cell enforces the borrowing rules at runtime. Borrowing rules at runtime instead of compile time. We'll cover interior mutability pattern where an immutable type exposes an API for mutating an interior value. Interior mutability, mutating. We'll also discuss reference cycles, how they can leak memory and how to prevent them. So there's possibility that memory can leak. Okay. And then here, so we have used boxt. When do we use boxt? When you have a type whose size can't be unknown at compile time, and you want to use value of that type in context that requires an exact size. When you have a large amount of data and you want to transfer ownership, but ensure the data won't be copied when you do so. When you want to own a value and you care only that it's a type that implements a particular trait rather than being of a specific type. Enabling recursive types with boxes using traits. Okay, chapter 18. That is using trait objects that allow for values of different types. So I'm just quickly going through things as we have covered this as to refresh our memory. As I myself, I admit I already forgot. So it's good to always go back. There's nothing wrong with that. And try to recall what was done the other day. Box T. Cover the syntax, the value stored within box T. Okay, so here box to store an I32 value on the heap. Okay, and B print line B here. Okay, so what does it say? Value of box points to value 5, so box points to an I32 5. Program will print B equals to 5. Can access the data in the box similarly to how we would if this data were on the stack, just like any owned data. Yeah, but in this case, it's going to be in the heap. Yeah, on the heap. Yeah. Just like any owned value, when box goes out of scope, B does at the end of main. It will be deallocated. So the only difference is with using box, it's going to be stored on the heap. So it says here it's not that very useful because it's only one value. Okay. Recursive types with boxes. Value of recursive type can have another value of the same type as part of itself. Okay. Then I remembered something. There's this cons list. Okay, so this one looks like a how should we call this? Yeah, it looks recursive because 1 will have this, then 2 will have this, and 3 will have nil. So the cons list nested pairs. Okay, nested pairs. List version of a linked list. Okay. I don't know Lisp. Yeah, but here it looks like this. Okay. A cons list isn't a commonly used data structure in Rust. Most of the time when you have a list of items in Rust, such as vector, is a better choice to use. Other more complex recursive data types are useful in various situations, but starting with the cons list in this chapter, we can explore how boxes. Let us define a recursive data type without much destruction. Okay, so you can do it like this, enum list. So here, this is also a list, and then, so this is the first part, and then this is the second part. I mean by the looks of it. First part, second part. Okay, let's see. Const, yeah, 1, and then you have another const, then 2, another const, 3, and finally nil. How that would look like? Okay, so it shows here there's compilation error. So recursive without indirection. Insert some indirection, example box RC up 1% to break the cycle. So it's suggesting to use box. Okay. Infinite size. Okay, let's see here. Computing the size of a non-recursive type. So you have enum message, you have quit, move, write, change color. Okay, let's see here. I think this is the diagram. Listing 15-2 needs, where's 15-2? 15-2. Okay, 15-2, this one. Okay. When Rust tries to determine how much space a recursive type like the list enum in 15-2 needs, the compiler starts by looking at the const variant, which holds a value of I32 and the value of type list. So there's a list. Therefore, const need an amount of space that is equal to I32 plus the size of the list. To figure out how much memory the list type needs, the compiler looks at the variant starting with the const variant. And this process continues infinitely. Yeah. Here. Okay, using box_t to get a recursive type with a known size. It says here we use box_t. Let's go straight to the implementation. Yeah, so I think the compiler was suggesting this earlier. You can see from here, box. Yeah, so box list. Use create list const and nil. So now it looks like this: const 1 box new, const 2 box new, const 3 box new. The const variant needs a size of I32 plus the space to store the box pointer data. Okay. Box pointer data. So it means the size of the box is always fixed. We have broken the infinite recursive chain. So the compiler can figure out the size it needs to store a list value. Why is that? Because the size of box is the reference, so it's always fixed. The box_t type is a smart pointer because it implements deref trait, which allows box_t values to be treated like references. Deref. When the box_t values go out of scope, the heap data in that box is pointing to a cleaned up as well. Is cleaned up as well because the drop trait implementation. Because of the drop trait implementation. These two traits will be even more important to the functionality provided by the other smart pointer types we'll discuss in the rest of this chapter. Okay, two traits in more detail. So it's like it flattens the the const recursive uh, data. Okay. Treating smart pointers like regular references with deref. Okay, deref trait allows you to customize the behavior of dereference operator. So that's the star. Okay. First, look at how dereference operator works with regular references. We'll try to define a custom type that behaves like box T and see why the dereference operator doesn't work like a reference in our newly defined type. We'll explore on implementing the deref trait makes it possible for smart pointers work in ways similar to references. Then we look at Rust deref coercion feature and how it lets us work with either references or smart pointers. Okay, so here is an example of my box. Where's the implementation? Box. Yeah, here. Defining our own smart pointer. My box, type T, and it will accept T here as well. So implement type T, my box. Okay, so here I have new. It returns my box T, my box X. We define the struct named myBox and declare a generic parameter T because we want our type to hold values of any type. The myBox type is tuple. It's a tuple struct with one element of type T. The myBox new function takes one parameter of type T and returns a myBox instance that holds the value passed in. Let's try adding the main function in 15-7 to listing 15-8, changing it to use myBoxT. Okay, myBox new. We tried this yesterday, the other day. Oh, I think we had it here. Okay, so it will not compile. Why it will not compile? Because of this. I think this is the dereference coercion. That's it. myBoxT type can be dereferenced because we haven't implemented that ability on our type. To enable dereferencing with the asterisk operator, we implement deref trait. Okay, so how do we implement deref trait? We have standard OPS deref. Deref for myBox. So deref is the trait. And then we are required to implement this function. Deref self target. So this one is the first element of let's say tuple. Yeah, tuple. Accesses the first value in a tuple struct. The main function listing 15-9 that calls asterisk on myBoxT value now compiles and assertion passes. And did we implement this yesterday? Yeah, it's here. When we entered asterisk y in listing 15-9 behind the scenes, Rust actually ran this code. So it's like asterisk y deref. Rust substitutes the asterisk operator with a call to the deref method. Deref method. Okay. So this one is actually calling the deref method. So the reference is here. outside the parentheses is still necessary, has to do with the ownership system if the ref method return the value directly instead of a reference to the value. The value would be moved out of self. Value will be moved out of self. We don't want to take ownership of the inner value inside my box T. In this case, or in most cases, where we use the dereference operator. Note that the asterisk operator is replaced with a call to the deref method, and then call to the asterisk operator just once. Each time we use an asterisk in our code. Because the substitution of the asterisk operator does not recur infinitely, we end up with data of type I32, which matches 5 in the assert equal. It goes in, and then it calls this one. What's the value of self? Self is T, the first element. Referencing the first element, so you get 5. But can we still use Y here? Assert equal 5 Y. You cannot use it anymore. No, cannot use it because it's a my box integer. If you use this, what happens? It will be the can't compare integer with ampersand my box. Consider dereferencing here. Asterisk asterisk. Why did it suggest asterisk asterisk? So you can only use one. Oh, it still works. Let's run this. So it's still equal to 5. Okay, so how about if we do something like this? Okay, that is the scope. Yeah, now this will complain. How about if we transfer it here? And it's still no, not assert, but can we do a debug asterisk y? Asterisk y is still 5. Well, it's good to know that we can do that. Okay, I'm not sure if we have covered this part here, but let's continue. Implicit deref coercions with functions and methods. Deref coercion converts a function to a type that implements the deref trait into a reference to another type. For example, deref coercion can convert $string to $str because string implements deref trait. So I think it was mentioned. String is a smart pointer also. Implements a deref trait such that it returns a reference to an str. Deref coercion is a convenience Rust performs on arguments. Deref coercion is a convenience Rust performs on arguments to functions and methods and works only on types that implement the deref trait. It happens automatically when we pass a reference to a particular type's value as an argument to a function, or a method that doesn't match the parameter type in the function or method definition. A sequence of calls to the deref method converts the type we provided into the type the parameter needs. Deref coercion was added to Rust so that programmers writing function and method calls don't need to add as many explicit references and dereferences with ampersand and asterisk. The deref coercion feature also lets us write more code that can work for either references or smart pointers. To see deref coercion in action, let's use myBoxT type we defined in 15-8 as well as the implementation of deref that we added in listing 15-10. Okay. Hello function that has a parameter name and type at str. Okay. Hello name. Deref coercion makes it possible to call hello with a reference to a value of type myBoxString. M myBox new string from Rust. Hello $M. That's the explanation here. Here we're calling the hello function. So there's a reference to str as how most of functions would have to be, because we're borrowing function with the $M. Okay, but now we are passing in, okay, we're passing in the reference to M, which is a reference to, okay, M is a reference to the myBox, the entire myBox string. Because we implemented the deref trait on myBoxT in listing 15-10, Rust can turn ampersand myBoxString into ampersand string by calling deref. How is that possible? Ampersand myBoxString into ampersand string by calling deref. The standard library provides an implementation of deref on string that returns a string slice. And this is in the API documentation of deref. Rust calls deref again to turn ampersand string into ampersand str or string slice, which means the hello function's definition. Okay, so this part here will convert string into ampersand string. That's what it was trying to say. If Rust didn't implement the deref coercion, we would have to write the code in 15-13 instead of the code, okay, 15-13. Okay. So without the dereferencing, it will look like this. Ampersand. Okay, the string slice. Ampersand of the value inside the reference of M with this range. Okay, let's see. The asterisk M dereferences my box string into string. Okay, so essentially this one is string like this. Then the ampersand and this one takes a string slice of the string. Okay, ampersand, so it's like ampersand of rust. That is equal to the whole string to match the signature of hello. Okay, because now it is a string slice. So it matches the signature of hello. Like this. We can try that out. Let's see. Okay, it's good. I haven't tried it yet, so we can try it now together. Remove this. Okay, so let us set M equals to, try to recall from my memory. My box. My box. Then here we have string, which is also a smart pointer from Rust. Okay, and print no. Here use ampersand M. So oops, not M, but M. What? Ah, no. We have hello. Function hello should take in s colon ampersand str. It's going to be a string slice. Oops. And we print okay. Let's run this one. Rust. Okay. So the explanation for that is Let's try to recall what was it without the deref implementation. So first we have dereferencing M. This one will return string, to return string. So that is okay, that is string. And then string, so if this is string, I will put ampersand because I'm borrowing it. Actually, this one will display Rust, if I'm not wrong. Let's see. Maybe I'm wrong. Let's see. Yeah, so I'm right. It's Rust because the range if you put one dot dot, yes. So starting from 1 onwards. So what? This is 0. 1 onwards is UST. See? UST. So if we remove this and just dot dot, it's still the entire thing. There. Rust. So what else? If we put dot dot until 3, so that is 0, 1, 2, 3. So does it mean it's only until S? So RUS. RUS. Yeah, RUS. So actually we can just remove this one. Still work. There you go. So if string and vect are smart pointers, something, I might be wrong, but let's try. Let say v equals my box. So instead of string, I'll put vec no, I'll use vec macro instead. Vec macro of having 1, 2, 3. Okay. Then hello, that becomes okay. So instead of hello, let's try function view. View what? View the content of you. Oops. Function of view can we put you here? You person reference of vec. No. Vec. vect, shall we put I32, so it's explicit. So for item in U, is correct. Print line item. Why do I need this one? No need. Just put item. Okay. Then here, view. I wanted to view what? To view. Some percent V. What's the problem with item? Item literal. Okay. Okay. So if you run 1, 2, 3, so it worked. Or another way of doing it. Let's copy this, put it here, comment this out. So if we start again by dereferencing, so put this one again, oops. I'll put this one again with an asterisk to V. Asterisk to V is actually the vector. Expected reference ampersand vector, you can see from here. So what we need to do is we just put this one because we need the reference to the vector so that it will match with this one. So this is sufficient enough. And when we run this, of course it will print 1, 2, 3. Yep. There you go. Okay. It's clear how deref coercion interacts with mutability. Similar to how you use the deref trait to override the asterisk operator on immutable references, you can use the deref_mut trait to override the asterisk operator on mutable references. So Rust does deref coercion when it finds types and trait implementations in 3 cases. From $t to $u when t, what are these? T deref target equals u. From $mot t to $mot u when t deref mut target equals u. Okay, so this one and this one reference, and this is a reference to a mutable. Okay, in this case it's a reference to a mutable t to a reference u when t dref target u. Okay, so in this case, dref target u, that's the difference. Dref target u, so they are reference to the target u. While here, dref mut, because this u is reference mut target u. This one is only a dref target u. Okay, so here. Okay. First two cases are the same except that the second implements mutability. First case states that if you have reference t and t implements dref to some type u, you can get a reference to u transparently. The third case, second case states that the same dref coercion happens for mutable references. Third case is trickier. Rust will also coerce a mutable reference, an immutable one, but the reverse is not possible. Mutable references will never coerce to mutable references because of the borrowing rules. If you have a mutable reference, that mutable reference must be the only reference to that data. Otherwise, a program wouldn't compile. Converting one mutable reference to one immutable reference will never break the borrowing rule. Okay, so it says here, converting one mutable reference to one immutable reference will never break the borrowing rules. So mutable to immutable. Okay, converting an immutable reference to a mutable reference would require that the initial immutable reference is the only immutable reference to that data. But the borrowing rules don't guarantee that. Therefore, Rust can make assumption that converting an immutable reference to a mutable reference is possible. Immutable to mutable, so that one is not possible. So can't make the assumption. Okay, let's move on. Running code on cleanup with drop trait. The second trait important to smart pointer pattern is drop. So we have already discussed dref, now it's drop, which lets you customize what happens when a value is about to go out of scope. Can provide an implementation for the drop trait on any type, and that code can be used to release resources like files or network connections. Okay, we're introducing drop in the context of smart pointers because the functionality of drop trait is almost always used when implementing a smart pointer. For example, when a box T is dropped, it will deallocate the space on the heap. Yeah, because we're talking about referencing space on heap. In some languages, for some types, the programmer must call code to free memory or resources every time they finish using an instance of those types. Okay, for some types, in some languages. Yeah. Examples include file handles, sockets, and locks. If they forget, the system might become overloaded and crash. In Rust, you can specify that a particular bit of code can be run whenever a value goes out of scope. Then the compiler will insert this code automatically. As a result, you don't need to be careful about placing cleanup code everywhere in the program that the instance of a particular type is finished with. You still won't leak resources. Okay. The compiler will insert this code automatically. So you can specify that a particular bit of code be run whenever a value goes out of scope. You specify the code to run when a value goes out of scope by implementing the drop trait. The drop trait requires you to implement one method named drop that takes a mutable reference to self. To see when Rust calls drop, let's implement drop with println statements for now. Okay. 15-4 shows a customer smart pointer struct whose only custom functionality is that it will print dropping. Okay. When the instance goes out of scope to show when Rust runs the drop method. Okay, so I think this is a good way of debugging the drop if it's being called. Okay, let's try this one. Smart struct custom smart pointer data string. You can just insert it here. Then implement drop for custom smart pointer. Okay, before we continue, let me just try to comment this out. Of course, drop the complaint that we haven't implemented the function drop. So let's see. Missing drop in implementation. So using Visual Code, it has some benefits. Then we can do a quick fix. Let's see. It added it. Yeah. So although there's a to do, we can just delete that. And then copy this over. Remove the comment. Remove the line. Essentially, it's still the same. But what's so special about this? You have a reference to a mutable self. Then dropping custom smart pointer with self dot data. So data is this one. Yeah. Okay. So we can remove this now. And then here, oops, the mouse pointer is jumping unnecessarily. Can copy this. Let's comment that out. Let's see. Custom smart pointer. Okay, so you have data of string my stuff, C, D, okay, so we're not using it, but after this, I think it will print. What will it print? Dropping custom smart pointer with data my stuff, then dropping custom smart pointer with data other stuff. That's what we should expect. Oh, other stuff. Is it doing it backwards? Again. Mm. Let's try to, okay, let's try to move this. Will it reverse the, will it display my stuff first and then other stuff? Oh, it did. Did. Let be consistent. My stuff, other stuff, stuff. Okay. Doing. Okay. So the drop rate included in the prelude included in the prelude. Where is it? So we don't need to bring it into scope. We implement the drop trait on custom smart pointer and provide an implementation for the drop method that calls println. The body of the drop method is where you would place any logic that you wanted to run when an instance of your type goes out of scope. We're printing some text here to demonstrate visually when Rust will call drop. What is a prelude? I think until now we don't know what prelude is. Maybe let's search it up. It's about time we should understand what this is. Rust, programming language, prelude. In Rust programming language, the prelude refers to a small, curated set of commonly used items from the standard library are automatically imported into every Rust program. This implicit import means that developers can use these items without needing to explicitly add use statements for them, making the code more concise and convenient for common. Oh, okay, so it's an automatic import. Items with the std prelude module are automatically brought into scope in every Rust module. Commonly used items, you have option, result, peg, string, iterator, and clone. Preludes, the Rust references. Oh, where is this? Oh, it's in the same, or is it different? Oh, this is Rust reference. Ah, okay. Okay, so I think we need to have this in our books. Let's see, I have shared doc Rust HTML book. Copy this and create a new duplicate. Where's prelude? Reference names preludes. Is it here? Doc Rust. So instead of book, I put preludes. Will it be there? Ah, it's there. It is there. Okay. Okay, then I can close this. And this one, I'll put it under Rust. Rust. There. Cargo commands. Cargo commands. So is it also possible if we duplicate this, instead of reference, put cargo commands? It's there as well. Okay. And now place this under this one. Yeah. Okay, this one is in my own directory. This one is online. Okay, maybe we can delete this one. Okay, so prelude is a collection of names that are automatically brought into scope of every module in a crate. Standard library prelude, external prelude, language prelude, macro use prelude, tool prelude. Okay, in different editions. External prelude. So there are differences. Okay, I don't want to read this now. At least we know that it's a curated list and it is already loaded. Okay, let's continue. The end of main custom. Yeah, these are the things we saw. Rust automatically called drop for us when our instance went out of scope. Calling the code we specified. Variables are dropped in the reverse order of their creation. So D was okay. Variables are dropped in the reverse order of their creation. This is what we have observed. So D was dropped before C. This example's purpose is to give you a visual guide to how the drop method works. Usually, you would specify the cleanup code that your type needs to run rather than print a message. Okay. Fortunately, it's not straightforward to disable automatic drop functionality. Disabling drop isn't usually necessary. The whole point of the drop trait is that it's taken care of automatically. Occasionally, however, you might want to clean up a value early. One example is when using smart pointers that manage locks. You might want to force the drop method that releases the lock so that other code in the same scope can acquire the lock. Rust doesn't let you call the drop traits drop method manually. So you cannot call it manually. Instead, you have to call the stdmemDrop function provided by the standard library if you want to force a value to be dropped before the end of its scope. Okay, so if you dropped it manually, does it mean that, okay, so if the struct implements drop method and you have already dropped it, what will happen? If you want to force a value to be dropped before the end of its scope, before the end of its scope, so I think it will complain. But this one is provided. If you try to call drop traits drop method manually by modifying the main function from listing 15-14 as shown in 15-15, will get compile error. Let's see. Data string C drop. C drop. Okay. C dot drop. see that drop. Okay, so it will not consider using drop function drop. Oh, I think we saw that, right? Drop C. Again, I think the auto completion already suggested C dot drop. There. How is this? Disposes of a value. This does so by calling the argument's implementation of drop. This effectively does nothing for types which implement copy. So the value persists. Explicitly drop the vector. I think the print would give us some hint. Let's copy this one. Put it here. And this one also. So what we have observed earlier is when we run this one without the drop, other stuff will be printed first. So it's calling the drop traits function here. So this one is printed first and then this one. But in this case, because we have manually called the drop of the custom smart pointer, so here it will print this, and then it will print dropping custom smart pointer with data my stuff, and then print this one, and then print this part, and then print other stuff. Okay, let's try. Yeah, custom smart pointer created, then it's dropping my stuff because of this, and then before the end of main, this one, and then this one was created again here, and then other stuff, this one. Okay, it is clear. The text dropping, okay, I think that one this is shown. Yeah, I think over here we did more than that. You can use code specified in a drop trait implementation in many ways to make cleanup convenient and safe. For instance, you could use it to create your own memory allocator. With the drop trait and Rust ownership system, you don't have to remember to clean up because Rust does it automatically. So Rust will automatically call the drop function if you implemented that trait. Okay. Now where are we? You also don't have to worry about problems resulting from accidentally cleaning up values still in use. The ownership system that makes sure references are always valid also ensures that drop gets called only once when the value is no longer being used. Now that we have examined box T, take a look at few other smart pointers defined in the standard library. Okay, so this one I wanted to try. So it says here, you also don't have to worry about problems resulting from accidentally cleaning up values still in use. So how about drop is here. Can we debug? C. Can we debug C here? Debug. Okay. Derive debug. Struct. Sharp. Derive debug. And here. What was that? Say like that. Already forgot. It's the error here. Use of move value C. Value C is already moved. We can how can we I wanted to do is, although drop is called here, but C is still being used. Let X equals to $1% C. Let's see. What happened? Dropping my stuff now is over here. Okay, because we're still using it here. We're borrowing it here. So drop did not happen. What is this? Cost to stdmem drop with a reference instead of an own value does nothing. Oh, it does nothing. Okay, but we cannot. I'm gonna do this. How can we say C is still being used? Drop gets called only once when the value is no longer being used. Only once. Okay, can we do something like this? It's just for illustrating that statement. So I'll put it within this scope. Yeah. So ideally, it will, after this scope, it would have been dropped. Then here, this will complain. Cannot find, okay, cannot find value C. Cannot find value C. Hmm. Print 9. Can we do something like this? Let's see. What if I will drop it here? So this one will complain. Use of move value. Okay. That's not what I wanted to manually drop it here to illustrate. Print C. Because if we put ampersand C here, of course we already know that we're just borrowing it. So drop with a reference instead of an own value does nothing. So it's like this did not happen. Okay, for the time being, let's run this one and see. It's the behavior. Okay, other stuff. Of course, other stuff would be last. Because my stuff is dropped here after customer created. And this is printed and then created. if we are still using it, so it will not drop, will not call the drop function. How about if we illustrate it this way? For example, here I will use C, debug C. What will happen? We printed out this one, then created, and then created the second one. This one, and then we have shown debug my stuff. Okay, in this case my stuff was deallocated or dropped first, and then other stuff. Because it's still being used here. No? I think that confused me. If we don't have the debug, of course other stuff will be displayed first. Comment that out. Other stuff, and then my stuff. We cannot put drop here also. If we put the drop here, of course my stuff will be executed first. Drop C. My stuff. Okay, so that's how it was behaving. What's the next one? RC reference counter. Reference counter. Let's see what we have. Is it long? It's one section. Okay, so maybe tomorrow we'll continue with the reference counter. The reference counted smart pointer. You know exactly which variable owns a given value. For cases when a single value might have multiple owners. Okay, so multiple owners. Let's take a look. Which one will have multiple owners? A cons 5 3 I think it has something to do with clone. Okay, RC is here. Okay, so let's go through this tomorrow. Okay, so thank you so much for joining me today live, and let's continue again tomorrow. But before we finally end, let me just thank my supporters.